Hello, my name is Hui, and in this video I'm going to talk about chaos in the Henon map and controlling chaos using the OG1 method. What is chaos? Well, chaos is a long-term behavior of any dynamical system that is aperiodic and deterministic, depending on the physical laws that are governing the system. It is also very sensitive to the initial conditions of such system. To put that into a physical context, a chaotic behavior can manifest in a nonlinear oscillator like the driven damped pendulum that goes by the equation of motion as written here. But for the purpose of my video, I would narrow my focus to the analysis of a Henon map. So this is the Henon map. It is a very well-studied classical map capable of exhibiting both periodic and aperiodic behaviors depending on the set of parameters and what initial condition that you choose. The Henon map that I'll be using throughout this video has this folding form and the parameters A set at 1.29 and B set at 0.3.
For now, let us set the initial condition to be at x not equal to 0.5 and y not equal to 0.5. Here's what the map traces out in the xy plane. The orbit in the xy plane as represented by the gray dots for this initial condition is chaotic because it does not trace out any periodic behavior. However, if we set x naught and y naught to be both at 0.8384, we see only one fixed point which represents a periodic behavior that differs from the one earlier. Hence, we can see why the behavior is sensitive to the initial condition. This is one of the two fixed points for this map. The fixed points in this map are unstable. There are two of them. And the stability of a fixed point for this particular map can be shown by looking into the Jacobian matrix of the map. The fixed point satisfies the following equations, and we will use these equations as a part of our chaos control algorithm.
We have some understandings of the Henon map. Let us apply some chaos control to it. The map that I'm applying chaos control to has the initial condition x naught equal to y naught equal to 0.5. Let's say at the step n equal to 3, I want to apply chaos control. The method I'm using here is called the OG1 method. At that particular step, we have this value pair x3, y3. Instead of proceeding the next iterate using the original map, I calculate a value a prime like a pseudo parameter that has this particular formula that is solely in terms of x3. A prime is actually treating x3 as if it is a fixed point. Afterwards, I compare a prime with a. If a prime is within a range rho of a, then we change a to a prime and then proceed the next iterate with a prime. However, if a prime is far away from a, then we continue with the next iterate using the original a. This method is repeated for every step, and for every step we compare the pseudo parameter a prime with the original parameter a, which has the value of 1.29. And this is the Mathematica code that I use for the algorithm.
Here is the control algorithm represented as a Mathematica conditional argument. In this plot, the range rho is set to be at 0.3 and the control is applied at n equals 400. Here's the xy plot, and here's the related 1D xt plot. And we see that it takes around 50 iterates for the plot to settle in a periodic behavior. If we lower the value of rho to 0.01, we still obtain the same desirable periodic behavior, but it now takes more than 3,400 iterates to settle. So the smaller rho is, the more time it takes for a system to settle. Overall, the method is relatively simple, and applying it in a physical system depends greatly on the extent to which you can tune your control parameter A. There's a limitation, however, as not all values of rho guarantee the same behavior. For instance, at rho equals 0.03, our original system settled to a very strange periodic attractor, as shown here. Therefore, the OGY method requires some predictions of rho based on the Poincare section of a chaotic attractor. The app demonstrated the OGY method of chaos control on a discrete system like the Henon map. The method, nonetheless, finds applications in various continuous systems. One of them, can be the driven damp pendulum, in which the control parameters that we can predict is the driving strength of the driving force. It can also find application in controlling oscillating chemical reactions and other oscillating systems. That is it for my video. Thanks for watching.